All right. Greetings and salutation, everyone. And my name is Fernando. And in the next couple of minutes, what I want to show is something related to this. So, breakdancing babies. So, well, not really, but to be serious. As most of you know or are familiar with, at the very early stages of development, babies play around their limbs, their arms, their legs, just to try to explore the world and to try to get information, make sense of that world. And indeed, this is the case for many animals. It's also the case for robotics. They have many sensors, and they are trying, at the very beginning, whenever we're thinking from this learning perspective, to make sense of this information. However, this stream of sensors, of sensory motor data, might be massive, might be difficult to pre-process, to post-process, to really make sense of. Our claim here is that behind the scenes, there's a hidden structure, an underlying structure that may help to understand the behaviors, or behavioral primitives, as we were calling, of what is the emergence of this interaction that you are seeing with a body. Now, in that sense, our motivation here, the question is, well, how can we extract this hidden structure? How can we extract these behaviors? How can we understand why they happen? Maybe how can we decompose it to have a better understanding of this? Our entry point to do this was inspiring the idea of sensorimotor contingencies. And I see that Kevin O'Regan is here, so please, if I say something wrong, slap me. So the idea of having this law-like relationships between actions and sensations. In here we thought, well, maybe we cannot go as in a very deep level and discovering sensorimotor contingency, but perhaps we can discover other types of sensorimotor relationships that can work as a proxy to detect a sensorimotor contingency. Like if I move my arm in front of my eyes, I can detect my arm. If I touch my body, I can have a tactile sensation and I can discover this association. So our goal here was to develop a framework in which an agent could discover its body's regularities using exploration. And the premise was simple. We have an agent, in this case, a very simple agent. It's just a 6 degrees of freedom system with 2 arms, with a torso. It is biologically inspired in the sense that it has some antagonistic actuation, and it has some very simple sensory system. It can detect its joint angles, so a form of proprioception. It is also equipped with some receptive fields along the body, so as to imitate the idea of tactile perception. And there's also a visual field. So basically, when the body is within the visual field, you will have activations in those blue pixels and emulating the idea of how vision would work. And to generate the sensory data, we need to have motion. And since we didn't want to go complex, we basically said, well, let's have motor babbling, which in very scientific terms is just move randomly and hope for the best. And indeed, we hope for the best, and we're saying, well, now we have a method to generate data. We have the sensorimotor stream already acting, already working. How do we start making sense of it? We follow the idea of dynamic functional connectivity, which was originally a technique that was applied in neuroscience with the idea of trying to detect what are the functional relationships, the statistical relationships between different signals measured from different regions of the brain. And so we basically imported this idea and translated it to the part of, well, let's try to find the sensorimotor dynamic functional connectivity. To do this, we started with the mutual information. Why? Because it's an information theoretic metric, very simple, that we can use to detect nonlinear relationships. If you're not familiar with it, all it tells you is that if you have 2 signals, then if you have high mutual information, if you know something about a signal X, you likely know something about a signal Y, at least to some extent. We have to do this for every pair of signals that are in the sensorimotor stream. Now, if in addition to this, we're doing with a shifting window, we can argue that we are computing an instantaneous mutual information, and in a sense, we're also having or capturing what will be the time-varying information sharing state of the sensorimotor system, which, as is illustrated here, well, you can interpret this as a matrix which is reflecting a graph, a sensorimotor graph expressing these relationships between the sensorimotor system. Now, at this point, we could say that now we have a form of dynamic functional connectivity, and we could start trying to draw some conclusions about what is the the behavior of the system, what it is doing, extracting some knowledge. However, at this level, it's hard because we're working at the signal level. If you have many signals, then extracting some information from them would be complicated. So we extract away one level and start looking for groups within those signals. And we apply another method called the infinite relational model. And all it is trying to find for clusters in those signals based on the relational information that was provided by the instantaneous mutual information. So now that you have your graph, which is shown here, so eventually you start clustering, and then within those clusters you can detect groups of proprioceptive signals, groups of visual signals, groups of tactile signals. But not only that, that would be this matrix, what is called Z, but you have also a matrix H, which would also extract the information from the time-varying mutual information matrix and would also provide another matrix, also time-varying, expressing what are the different relationships across time between the modules that the infinite relational cluster was able to find. So in a way, also another form of dynamic functional connectivity. When we apply this to our system, we were able to determine about 23 functional models. I'm saying about 23 because this is a stochastic process, and every time you run it, you will get small variations. However, they were consistent more or less in the size and groupings of the clusters, so which is what you can see there on the right. You have also here a depiction of how these graphs would evolve in time. And what's nice is that now you have a definition of how these groups of signals are interacting among each other. But you could also express this graph, sequence of graph, as a matrix, which is what you see on the right. This matrix H, it's also practical because then you can study it further. Now that you have these relationships, perhaps you can look for patterns that appear in time that maybe that are recurrent. To do this, we use the technique called non-negative matrix factorization, which, well, the why is because we have the relationships and all of them are positive because they are coming from the mutual information, which is also providing positive values for the connections between the signals. So since we have this constraint, then non-negative matrix factorizations allows us to do that. Another important fact of that is because we can decompose these patterns, and those factors that we extract from the mutual information matrix will give us factors that are independent from each other, acting as a basis. So basically a number of basis graphs, which you could say that if you add them together, you can find what is the pattern of behavior that you were seeing at that moment in time. For example, the factors that we found, this is a representation of that, so it was 25 factors. In here we are color coding them because at some point those factors have some more influence in the proprioceptive system, or more influence in the tactile events, or more influence in the visual field. The idea then is that with these factors, you can basically do a weighted sum, and for any given point in time, you can reconstruct what was the interaction that the system was exhibiting by just summing these factors using what we call the scores. And basically, this was the idea. So this is a time-varying thing. When you have the scores, eventually, just sum the factors, find what is the behavior that you were experiencing. So in general, the framework that we put together was basically that. We have a system. The system is basically exploring the world using some random motor babbling. You are collecting signals. Then we are analyzing the signals in the form of the instantaneous mutual information to create some dynamic functional connectivity. We go a level above to compute the infinite relational model, and then compute another form of DFC, but at a cluster level. From there, we extract patterns using the non-negative matrix factorization, and this is pointing at what are these behavioral primitives that we are observing in the system. So when you see this in action, this is just an example of how the system was doing the exploration, the motor babbling. At some point, you can see that there are some tactile events when the robot is touching either the hands or the torso. You can see that this is very well reflected in the mutual information matrix, which is at the top right corner. Whenever it lights up, it's basically because the sensorimotor system is excited. So there's a lot of information that you can try to draw some conclusions from. And in the bottom, you see what are the main factors acting at that point. That means the most important behavioral primitive that was basically producing this behavior. And what you see in the right is sort of waves. It's just the scores. That means what was the most relevant factor weighted by the score that took place at that given point in time. So basically, blue is vision, red is, blue is vision, red is touch, and green is proprioception. And so you can see that everything matches according to what you see in the upper left corner. So to conclude, in our framework, which was a combination of these three main methods, the IMI, the instantaneous mutual information, the relational model, and then NMF, was indeed capable of giving us some information about some behavioral primitives of what we see in the behavior. So these 23 modules, functional modules, were able to represent this and capture this information, which was also then eventually distilled in these 25 behavioral primitives given by the non-negative matrix factorization. And we could see that it was a rather compact representation that was basically allowed us to explain what we were observing in the real system. So indeed, we can say that from chaos, we have some behavioral building blocks. And to finalize, just providing some outlook, and this is very well connected to some of the talks that we had in the previous sessions. Yes, we could have some more information about the motor commands, whether in the form of like muscle twitches or muscle contraction, maybe even torques. We could have a goal-driven behavior. At this point, we only have motor babbling, but we could have the mutual information serve as a metric in a way for a reward, for example, in reinforcement learning or any other sort of metric to drive the behavior of the exploration so you can eventually determine more informative factors. You can also apply the same methodology for infant recordings, like the session that we saw in the morning with the onesies. So definitely it could be extrapolated on that and perhaps also lead to some interesting conclusions. And finally, it could also be applied for other methods like in robotic manipulation, where you're trying to see if whatever primitive, whatever policy that the robot is following is also providing a given pattern of sensorimotor relationships. So with this, I conclude. Thanks a lot for your attention.
Okay, thank you very much. So I can take one or two questions. Do you have? Yeah. Where? Ah, okay. Where?
Thanks a lot. Very nice, interesting work. So I'm curious if it is possible to include high-dimensional sensory information. And second question, two questions. Is it possible to create a hierarchy of behaviors in your framework?
Okay. Well, yes, it is possible to have high dimensionality. The only problem is the cost of computation, because since the mutual information that we are capturing, we are doing at a small time windows, and we have many signals, then basically this explodes whenever you have a large number of signals, which would definitely be a major issue when you're trying. So better computationally efficient ways of computing the mutual information, or maybe any other alternative metrics, would be an alternative here to substitute in the framework. And about the second question, definitely yes, you could talk about a hierarchy when you look at the decomposition of the factors themselves, when you will have this scores that I was talking about, and these are telling you how important a factor was. So at some point, for any given point in time, you can say that which one's the factor was contributing more to this behavior, or in general, you could talk about like the mean behavior, which was the factor that was more present during the whole exploratory process.
Thank you. So, do you have any other questions?
Thank you very much. So, in the end, 25 of these patterns emerged. So my question is, why 25? What can you do with them? And are they related, and in what sense, to kind of real behaviors or?
Okay. Yeah, this 25 factors is because we were trying some numbers. At some point, we did some studies about whether bringing more factors would explain more, or would be able to reconstruct more this matrix of the evolution of the clusters. So since non-negative matrix factorizations in the end is an approximation, so it's just a factorization and it's trying to approximate the original matrix. At some point, adding more factors is really not bringing substantial approximation of the original part. So at this point, 25 was the sweet spot for in the compromising computation and what was the reconstruction capabilities of that. And what you can do with the factors is basically explain different behaviors at some point where you see that the robot that was waving the hand in front of the visual system, or it was doing just tactile exploration between just touching torso or touching only the hands or touching the arms. That's when you can see what the contribution of the factors. Of course, whenever you are combining this with the information about the scores, then you basically, it's like decomposing what you see, the state of the robot in a particular scene, decompose in different, what we call this behavioral primitives, and just like give you this understanding that eventually with this, you can reconstruct different behaviors and even probably motivate the system, like say, oh, okay, I want your exploration to look in general in a mean sense to that factor. So basically, which means, okay, just explore the left side of the body, well, the right side of the body, and or just explore the torso, or maybe just don't touch anything, but explore the visual field. Things like that could be possible.
Okay, time is up. Thank you very much.
Thank you.